Okay, so starting part B of homework 5 for process dynamics and control, the last part of the homework, we will be deriving algebraically the amplitude ratio and phase lag for a proportional integral PI controller, and we'll be explaining why a first order system with a PI controller will always be stable, whereas a second order system or first order system with time delay may not be as stable for some controller parameters. So I want to kind of draw out first and start with the kind of a schematic with the different types of transfer functions and kind of flows and what each one is equal to. So kind of we're able to visually see kind of what this controller really is intended for. But starting with the initially our first we're gonna change this pen thickness. Starting with our first line of flow, which is essentially starting with our set points, going to into this, our positive negative right here. We will also end up going to GC, which is essentially our first, essentially our transfer function, but for our controller, which is going to be labeled as GC. Another way to look at this is essentially it's a representation of gain, which is essentially KC, our gain for our controller. And then this is going to be going to our GP. And this equation is going to be denoted by K divided by tau S plus 1, or S can be also denoted by what do we call it? J omega. Okay. And then this is going to be our kind of outlet flow right here. And again, we're going to circle back with a recycle stream and our GM, I believe. Yeah, GM. And in this case, it's just going to be equal to 1. So we can go ahead and give it that equal to 1. Okay. And then we're going to come back here. And again, we know from our previous parts is that this function right here is going to be multiplied by this outlet flow here, which is y. And essentially that's what our regular cycle stream is coming back into this right here, right? So I want to go ahead and first start. We can't really explain this without kind of going through some previous steps, and that's going to be starting by deriving a amplitude ratio and phase lag for our proportional controller at RPI. And so we're going to first start with a overall equation for our GC, overall GC equation, which is essentially going to look like this GC in our essentially our sorry, what's that word called again? Our in our Laplace domain, which is equal to our Kc, which is our gain for our controller, multiplied by 1 plus 1 over tau s. And again, we know that s is equivalent to j omega, so we can go ahead and rewrite this as Kc multiplied by 1 plus 1 over j omega. Yeah, just j omega. Or no, tau j omega, right? Okay, so moving on from here, again, from all our previous parts of our homework in part A, what we did essentially is we kind of got developed or derived an equation for our transfer function, whatever it was, and then we ended up getting an amplitude ratio. Again, the amplitude ratio is going to look similar to what we did in the other parts, and it's going to be denoted here as AR equals, and our KC is going to be left outside of our square root function right here. And in this function, it's going to be 1 plus 1 over omega squared tau squared. Okay. So from this point, we know we have our amplitude ratio, and we're also looking for our phase lag. So phase lag. So at this point, looking for our phase lag, we know it's going to be denoted by our phi essentially, which is our phase lag. And like what we do in the other parts, it's going to be associated with our identity properties. So we're going to be using tangent in this case, or inverse tangent multiplied by 1 over omega tau. Okay. And essentially, let's go ahead and I'm going to erase this. Try to move some stuff around, but okay. So essentially, these are the um, two equations for us that we're trying to kind of derive. First off, our amplitude ratio and our phase lag. Okay. So now let's go back to our problem statement. What are we looking at? We're explaining why a first order system with a PI controller or a second order system or a first order with time delay, which ones are more stable, which ones are not. We know that a first order with a PI controller is essentially more stable, will always be stable. So let's go ahead and kind of descriptively kind of explain why. So first order, kind of finish with our derivations at this point. We have our first order with controller. We have our first order. We have our first order with our I think believe phase lag with time delay. Sorry. Okay. And we have our second order. Okay. So essentially we know that our first order is more stable. So let's go ahead and I'm gonna come back to that last because that's kind of the cherry on top. And kind of why we're doing this. And these are unstable technically. So essentially for our second order, let's start there. We essentially are adding a controller and adding a controller essentially to a second order. You end up with a delta that is equivalent to zero. And essentially, if we have a high gain or whatever, a high gain or K value, it can become unstable. So essentially, because we were introducing the phase lag and it has high gain, which can kind of lead to underdamping, not overdamping. So that is essentially why it becomes unstable for the case of a second order. Now, a first order with time delay, why would that be different than a first order with a controller? So essentially a first order with a time delay or a first order with, phase lag. I know other homeworks we explained how this was unstable when we added a controller, but it can actually cause phase lag. Uh, but what I guess the phase lag in general essentially causes the system to reach a degree of 180 or pi or what we did in the other homeworks. And an inverse tangent is essentially going to introduce instability, right? We're working with these degrees and radians, and when we're looking at something with phase lag, we looked at our kind of phi function right here, right? We're introducing a tan negative function. In that case, when we're doing that, it reaches on instability. So keep it short and sweet for our last one. A first order controller with for our first order with a controller will essentially always be stable from one simple true fact that it's never going to reach 180 degrees. I think that's the one thing to take from this video is that when a controller is introduced, it becomes stable because of that fact that it never reaches 180 degrees. Okay, so we're going to go ahead and move on to the second part of part B for this homework. We're going to be using all of the different parts in part A, as well as the part in homework part B, to kind of go ahead and put this all into Colab and see how it works when we go ahead and code it and make some subplots and kind of see this all visually. But yeah, that's it for this video. Okay, so starting part B of homework 5 for process dynamics, we're gonna go ahead and kind of explain some of these kind of inputs that we have from Colab and stuff like that. But yeah, we have our usual from the last part. So I know we were using sim, PID, TF1, Bode, all these stuff right here. Still using make subplot, SymPy, solve IVP, root, minimize. So nothing's changed regarding that. We're still importing our Chemi tools folder from GitHub. Um, I don't believe there's any other inputs. But yeah, let's go ahead and read the problem statement for this. For first part of part B, we're going to be deriving algebraically the amplitude ratio and phase lag for a PI proportional integral controller. And we'll be explaining why a first order system with the PI controller will always be stable, whereas a second order or first order system with time delay may not be stable for some control parameters. So I'm just going to read that. We're working on second part for this, but going ahead and reading that just kind of explain like what we did from the last part using those PI controllers, which ones are stable, which ones are not, because when we actually create this Bode diagram, it'll kind of make more sense based off of some of the transfer functions that are inputted that we know which ones are say stable. We'll end up creating a graph or a Bode diagram, and we kind of want to see when our function goes to one that it kind of goes down the function and it becomes unstable, right? All right, so for this part of the homework for a FOPTD model with the gain of 1, time constant of 1, and time delay of 0.1, we will be determining the optimal PI controller gain and reset time using the ITAE integral time weight absolute error criterion. And I went ahead and inputted these. We're going to go ahead and get into these in just a second. But we'll be making a plot of the Bode diagram showing that the calculated controller parameters lead to stable closed loop response. And then again, we will make another plot of the response of the system to a step change in set point. So this will be kind of split up between two different parts per se. We're going to first focus on kind of creating that first closed loop response. So making that first plot of the Bode diagram. But yeah, let's go ahead and you can see my screen here. We're looking at some of these criterias. For two new relationships based on this ITAE, so integral time weight absolute error criteria. We have three different kind of popular errors. The first one being the integral of the absolute value of the error, so IAE, and then we have the integral of the squared error, and then we have the integral of the time-weighted absolute error. So we're going to be focusing on this third one. For the problem statement, we'll be using ITAE to determine the optimal PI controller gain. Okay, so that's should sum up that. But yeah, so looking at our next little chart here before we go ahead and start our code and put some of those inputs in regarding this actually. For this, we're looking at a table that shows inputs, controllers, modes, and a kind of constant function value of A and B. So of course for input, we're looking at disturbance and set point. And then for our controller, we're looking at PI and PID, as well as our modes of P and I and D. So let's go ahead. I don't think there's anything else, but here's a little thing to note for set point changes. There's a design relation for the integral mode is this. So I don't think we'll be needing it for the second one, but might be, but we'll see. All right, so going ahead and starting with our first line of code here. There you go. All right, so we'll be starting with some inputs for this. So we're going to be specifically looking at our modes in either our A and B and setting some constraints here. So looking at specifically our set points for this, let's say we're setting up a function of PA and PB. So looking at our little chart here, you can see my cursor. We're going to be looking at it at 0.586 and negative 0.916. Let's go ahead and set that. And we'll kind of just need to set the 0.586 and then negative 0.916. Okay. So now that we have that, let's go down just a line, and we're going to be using this for our I modes for our set puts of PI, not PID still. So we're looking at IA and IB, and for these, it's going to be 1.03 and negative 0.165. Okay, so don't let the little exponents confuse you. We're just taking the constant value itself. Okay. Go ahead and run all this. Okay, so we look good. We're gonna set up some inputs. So the first input being k, and that's just gonna be equal to 1. And then we're gonna set up tau, and in this case, tau is also gonna be equal to 1. And we can also set up theta, which is gonna be equal to 0.1. Okay, yep, looks good. Let's go ahead and shift into that. Okay, so now what we want to do is we want to set up omega, and like what we did for the previous videos, we're setting up omega based off a logarithmic scale. So when we create this Bode diagram, it's going to be based off of a log or a logarithmic scale. So make sure to actually define this constraint early on, and this will be within our omega. So W equals MP dot log space. So it'll be from -2 to 1.5 and then to 1,000. So essentially 1,000 time steps, and this logarithmic is going to be from 10 to the -2 and 10 to 1.5. Okay, so we're then going to set up y, and y is essentially our kind of intermediate between all of our kind of gains and our new tau value that we'll set up. So setting up y, and in this case, it's going to kind of it's going to be based off of our kind of time inputs and our model controllers that from the ITAE. So kind of this little chart right here, we're looking at our modes and kind of basing this off here. And of course, our tau and theta. But starting off, it's going to be PA. So PA, that a constraint that we set up earlier, times theta divided by tau. And then this will all be to the power of PB. Okay. So now we can set up our KC value. So this is essentially the controller gain value, and it's going to be denoted by KC so that we know we're specifically referring to our controller here, and this is going to be equal to Y, that constraint, that our definition that we just set up, divided by K that we also set up. Okay, so now looking at our new tau value, we need to set up a kind of a new tau value based off of our old tau value, and that's just going to be denoted as tau I, and that's going to be equal to tau divided by, and then in this case, we're going to be using our I modes instead of our P modes. So first starting off in this bracket right here, we're looking at IA plus IB, and then this will be multiplied by uh, theta divided by tau, theta divided by tau. Okay, so let's go ahead and shift into that. Okay, so now that we have that kind of finished, we can go ahead and set up all of our transfer functions. And of course, all of our transfer functions, we're looking at all the ones that we kind of designed in that loop that I created in one of the other, I think the first part for this. So we're going to kind of be breaking these down and see how they're all connected within each other. So starting with the first one, which is essentially GP, and this is going to be referring to our transfer function of the process or a function of first order with essentially time lag. So this is going to be equal to, and we're going to be just basing this off of the equations that we set up on the other part. So we've already solved for this. Let's go ahead and just input it in. So it'll be exponent of negative theta times s. So I don't think we've set up this function. We can go ahead and pause this. Okay, so we'll actually, I was wondering if we needed to define what S is, but because we imported all of those notebooks, we actually have already done that. So let's just go ahead and now multiply this right here by K. Um, yeah, multiply this by K and then divide all of this by tau times S again, and then this will be plus 1, right? Yep, yeah, that looks good. Okay. So now that we've set that up, we can do this for our transfer function, essentially for our controller. So of course, this is gonna include what our value of KC is. We set up K for GP and we set up KC for GC. So doing this, we're going to be looking at KC times in a and then bracket 1 plus 1 divided by tau I times S. Okay. All right, now we can go ahead and set up our GM, our measurement, or just our last transfer function, which is just denoted as G1. And this is just going to be equal to 1. I remember in one of my videos, I was creating that loop and we had an equation for all of them, but we actually just set GM equal to 1, which was kind of just our recycle back down and up. So yeah, all right, we now want to kind of create a transfer function that kind of includes all of these. So we're going to be denoting this by GFB. And of course, since we're including all of these, we have to include GC, GP, and GM. So we're going to be equaling this to GC times GP. And then this will be divided by 1 plus GP, or I guess it doesn't matter which one starts. GP times GC times GM. Okay. All right, cool. I think that looks good. All right, so last thing for this is we want to make this function of GFP simply easier to work with. So we're gonna just be simplifying this function using our simplify function. So GFP is going to be equal to simplify GFP. Okay, let's shift into that. All right, so it looks good. We'll now want to set up kind of our Bode diagram, our actual function and plot itself. And we're going to want to be making sure that we kind of set these functions equal to, first off, our amplitude ratio and our phase lag to make sure that we're actually solving for that. All right, sorry, my camera fell. But continuing this, right? So we're wanting to just set our first one to an underscore, simply saying that kind of that's we're kind of skipping that essentially. So then we're going to be looking at our amplitude ratio and our phase, or I believe this is just going to be phase. Okay, I hope so. And this is going to be equal to Bode and then of GC times GP times GM and our omega function. Okay, before I finish off, I want to make sure that our phase is not capitalized before we move forward, so I don't want to mess anything up. Okay, so yeah, we're good. Our phase is not capitalized. So we now want to go ahead and actually create all of our subplots. So starting off with this will be fig equals make underscore subplots, and our rows are going to be equal to 2, and our columns are going to be equal to 1. Okay. And then we want to essentially add a scatter here. So fig that add underscore scatter, our x is going to be equal to omega, our y is going to be equal to our amplitude ratio, and our row is going to be equal to 1, and our column is going to be equal to 1. Okay. We now want to update our x and y axis. This is what we done from the last part. So it's pretty much we want to update it on a logarithmic scale. So fig dot update yeah, underscore x axis. And then so our type is going to be equal to log. And then our row is going to be equal to 1, and our column is going to be equal to 1. Okay. All right, so I'm going to go ahead and just copy and paste this because we now need to do this for our y axis. So let's go ahead and change this to y. Okay. So we then want to go ahead and add another scatter. So fig add underscore scatter. Again, we want to set our x equal to omega. We want to set our y, in this case, equal to phase. And then our row equal to 2 and our column equal to 1. Okay, so that looks good. We then want to update our x axes. However, um, uh, we want to change our row, and we're only going to be doing this for our x-axis. So let's go ahead and copy and paste this, and then change this row to 2. Okay. We then want to go ahead and update our layout. So fig.update underscore layout. And then we want to set up our height equal to 600, our width equal to 400, our template equal to plotly underscore dark, and then our show legend equal to false. Yep, that looks good. And then we want to set our second y-axis, and we want to essentially be setting up its tick marks. So doing that, we put our dict function and then d tick actually, and then we want to be setting this equal to 30. All right, so with this, we also want to set up a range. So for our range, it's going to be from negative 270 to 0. Let's go ahead and shift into this. Okay, so this looks good. First things first, I want to say that this is based off of a logarithmic scale, right? So we have our amplitude, we have our omega with our amplitude, and then we have our phase lag. And I remember talking about in a previous video that it's based off of linearization. So because we have a linear line here, we know that we're looking at looking at something correct per se. And then specifically this phase one down here, I wanted to say that we were looking at these different kind of types of when something is stable and not stable, right? So let's go ahead and see when this value kind of turns to 1, right? And I remember the last video that we kind of looked at when this value turned to 1, we started to notice some decay, which essentially meant we were becoming unstable. So see right here. So right here. So it's essentially steady and it's kind of linear almost on a horizontal side, and then it starts to have kind of variable decay. But you can notice that like the numbers even get more like kind of random as like the decay gets even stronger. So but yeah, that looks good. Let's go back and we have our question up here. So on my monitor right here, I put up my question. So with a gain of 1, time constant 1, time delay of 0.1, determine the optimal PI controller gain and reset time using our ITAE, became a plot of the Bode diagram showing that the calculated controller parameters lead to stable closed loop response. Perfect. So yeah, that sums up our plot of this Bode diagram. Let's go ahead and make another plot of the response of the system to a step change in set point. All right, so moving on to the second part again, let me just repeat that. We can now make another plot of the response of the system to a step change in set point. So doing that, we're gonna first start by kind of setting up our T and Y, and we're essentially setting up a simulation. So we're gonna be using our sim function, and then this is gonna be for that transfer, kind of that combined transfer function that we made earlier, GFP, and then this is gonna include our lambda function for 1, and then we can also just, or we can kind of, there you go, and we can set this our n here equal to 100 and our dt equal to 0.1, a time delay. So yeah, okay, let's go ahead and shift enter that. So we want to go and so we want to finally now create our subplots. So start by sending this equal to fig2 because we already did fig, and this would be make underscore subplots and fig dot add underscore scatter. And we're going to be setting our x equal to t in this case, our time, and then our y equal to y in this case. All right. So we want to then go ahead and update our layout. So fig.update underscore layouts. And we'll want to go ahead and set our width equal to 600 and our height equal equal to 400 and our template equal to plotly underscore dark. Go ahead and shift enter that. Ooh, no, has nothing on the graph. Okay, here we go. Pick two. Okay, perfect. So as you see, the whole point of this is making a plot of the response of the system where it kind of reacts to a step change regarding to the set point. So as you can see here, we have our time, we have our Y graph, and in a span of 8 seconds, it doesn't even hit 2 seconds for our actual process to kind of react to and cause a step change. Actually, it if you kind of look over here, it really only takes 1.5 seconds for a system to actually respond to this and our step change to actually happen, which is really, really quick. So definitely a success. All right, that finishes off our homework 5 for process dynamics. Probably not my last homework. I still have to do separations. So we'll see you there.